Okay. Okay, let's go ahead and get started here. Can someone in Pittsburgh please wave if you can hear me?
We hear you, sir.
Okay, great. So let me begin with a few announcements. First one I think everyone will be happy with. I've already dropped it over here, and most of you have probably noticed if you looked at Blackboard. So it turns out there's an MSCF policy not to give homework that's due during the week of exams. So as of now, there is no more homework 7/trading exercise that is due for a grade for the course. So hopefully that's good news. The only downside is there was actually some trading strategy development material that I would have liked you to have seen. So what I will do is I'll go ahead and post the exercise anyway, and those of you who feel particularly inclined can go ahead and do that in your incredibly large amount of spare time once all the exams are finished. So yeah, main thing is no more homework 7 or trading exercise. As a result, the 10% that would have been the trading exercise is lumped in with the rest of the homework. So the 6 homeworks you've done will count for 50% of the grade, and the exam will count for the other 50%. So 6 homeworks, 50%, exam is the other 50%. Secondly, I'm going to basically plan to finish up a few loose ends today. So that will be something I kind of forgot to mention on the way through because, well, it's not really that important since you know how to do the modeling, but it turns out you can label a lot of the things you've been doing as doing ARIMA modeling as opposed to ARMA modeling. So I just want to comment on that briefly. Then I'll do a bit of discussion about Arch and Garch models, which are these conditionally heteroscedastic models that help describe volatility. And then I'm going to finish up the day by going through what you're expected to know on the exam and have a kind of quick discussion of what's fair game and what's not fair game. So that's the plan for today. With a bit of luck, we should finish a little bit early. We'll aim for a bit over the 2-hour mark, but we'll see how we go. So before I start, does anyone have any questions about anything?
Yeah, I want to ask a question about the homework you gave us last week.
Okay.
And I wonder why, well, actually I want to ask what you put on the hint for the problem 2. And I couldn't really get why that reasoning follows.
Okay, so as a homework discussion, maybe we can take this offline. I'd be happy to discuss this offline. And the other thing is we'll also be posting solutions fairly soon. So I think, rather than, I'd sort of prefer to concentrate on exam discussion and the remaining material today. But yeah, I'd be quite happy to have an offline discussion on this. Okay. All right. Yep. Okay. Anyway, solutions will be posted fairly soon. The other thing, actually, I should have mentioned is a practice exam will be posted fairly soon. I'm planning on doing that this evening. So if it's not there by midnight, I'm officially telling you that you can all send angry emails to me asking where the practice exam is. I'd strongly recommend going through the practice exam before the real exam. It's going to be very, very similar in format. You should basically expect it'll be mostly questions of a theoretical nature with a little bit of interpretation of output. So if you can cruise through the practice exam fairly comfortably, I think you should be in reasonably good shape for the real exam. Okay, any more questions? Keeping in mind that I'm going to cover I'm going to discuss the exam a bit more once we've finished off the material for the course.
Are you going to provide solutions with the practice exam?
No, so rather than posting solutions with the practice exam, what we'll do is have, well, okay, I'm going to say yes. We will post solutions, but they're not going to be very nice solutions. They'll be kind of ugly, sketched out solutions. But we will be happy to interact. If you send emails to the TAs or me, we will discuss solutions, assuming that you've made some attempt already on the exam.
Thank you.
Okay. Anything else? Okay, so in that case, let me get back to course material. Sorry, I just had to remember this is slightly different from the Pittsburgh setup. So you can indeed see the document camera, right? I guess, yeah, you're seeing that. Okay, so first thing is something definitionally that I kind of skipped over before, and that is the notion of something called an ARIMA model. So you know who ARMA model stands for autoregressive moving average model. ARIMA model, the AR still stands for autoregressive, MA still stands for moving average, but this I here stands for integrated. And the definition of an ARIMA model is really very simple. If we can take a process, xt, and we difference it d times, so remember, superscript d means differencing d times. If it was a subscript, it would be differencing it lag d. So let's say we apply the differencing operator d times to xt, and we end up with another process, yt, and this resulting process, yt, is an ARMA PQ process. Then we say that xt is an ARIMA PDQ process. So really it's very simple. It just says that if you have to difference your series once in order to get your ARMA PQ model that you then fit to the different series, then what you've effectively done is fit an ARIMA P1Q to the original time series. So in the context of lots of the analysis that we're doing, we often have a price series. We then take logs. We then difference. By taking logs and then differencing, we've got the log returns, and then we usually fit some kind of ARMA model. Let's say we have, for example, an ARMA 10 or an AR1. Then this would be equivalent to fitting an ARIMA 110 to the series before we took the differences. In other words, the logs. Okay, does that make sense? Yeah, go ahead from Pittsburgh.
I thought you said that it wasn't good to take multiple differences. Didn't you say like 2 is okay, maybe, and then after
yeah,
that it's...
That's correct. In general, so ARIMA models in general can be dangerous models in terms of the quality of their forecasts. So as a general rule of thumb, if you see an ARIMA with 1, that's fairly typical. If you have the middle term there equal to 2, you might start to get worried that it has been over-differenced. If it's 3, 4, or more than that, you've probably got some dodgy analysis going into it. So yes, that's correct. In general, we do want to avoid over-differencing, and ARIMA models have this kind of differencing built in, and yeah, you should keep in mind that an ARIMA model with a large value of D is going to be quite unstable in forecasts going forward. Okay, was there one more question here, or is that all clear? Okay, so I guess the point is, when you hear the term ARIMA model, it's just an integrated version of an ARMA model. In other words, something that you difference to get an ARMA model. It's really just a definitional thing. We've seen in the course basically the kind of techniques that you can use to fit ARMA models. And really, an ARIMA model you're just explicitly saying how many times you difference the series at the beginning as part of the order of the model here. Okay, so that's a definition of an ARIMA model. But generally, in many cases, when you look at financial time series, you just go straight to the log returns. And for the log returns, you're generally not going to be differencing them. So you'll typically be fitting some kind of model directly to the log returns. So talking about using an ARIMA model is a bit of an artificial construction, really, on top of just the standard things that you do.
A question here.
Yeah.
When you say fitting a log return difference, what about in a bear market? If the market trend is down and you take a log, do you get a stationary?
No. Okay. So strictly speaking, if you have a permanent bull or bear market and there's a drift up or down, then when you take logs, you're going to get something with a drift. So then you difference to remove that drift. And if you did have a trend up or down, then this ARMA model you fit here will have a non-zero mu. So if you want to be precise about that, what you would do is you would... okay, so this raises kind of an interesting point. Let's say you difference and you end up with an ARMA PQ model with a non-zero mu. That's still stationary. It just has a non-zero mean. You could make the mean 0 by differencing again, but that would be bad because then you're getting into this realm of over-differencing. So in that case, this would be an ARIMA model, and you would explicitly specify. You would say where the underlying ARMA model has mean of x. You would want to explicitly say it that way. Does that make sense? Did that answer your question?
Because, I think originally, if you have the time series going up, it's almost like exponential, and you take a log, it's like inverse function, so you get a constant level. Is that true?
Well, okay, so if you have exponential growth in your original price series and you take a log, then it will become linear growth. So that's non-stationary. So you wouldn't fit an ARMA model directly to the log. You would difference once. And if you difference once to get rid of that trend and then fit an ARMA model, now what you've done is you fit an ARIMA P1Q to the log series. This is log series before it became log returns. Does that clarify a little bit? Okay. Yeah, so again, it's kind of mostly language. You generally know what to do now. You're generally fitting ARMA models most often with a zero mean, but sometimes with a small non-zero mean to log returns of price series. And that's the same as fitting ARIMA models to the logs. Okay, so now I want to get back to arch models, which I discussed a little bit last time. So I want to pick up, I'll just reiterate a couple of important things. So an arch model with mean 0, which is usually the way you define them, is something that satisfies xt as sigma t zt. The Z process here, which we usually take to be a white noise process, in the context of arch and the soon appearing Garch models, we say it's IID normal 0, 1. So it's a stricter requirement. But what we have is this recursive way of coming up with the sigma t squared term, and that is it basically just depends on recent data. So it's a constant alpha naught plus a sum j equal 1 to p, alpha j x t minus j squared. Now we had these constraints that alpha naught is strictly larger than 0, and alpha j is greater than or equal to 0 for j equal 1 up to p. We also require that the sum from j equal 1 to p of alpha j is less than 1. So we put these constraints on the thing in order to ensure stability. In fact, those constraints ensure causality And this is a special kind of causality, which is a bit different from the previous causality we talked about. Namely, causality here just means that you can express xt as some nonlinear function of zt, zt minus 1, and all of the z's prior to that in time. Okay, so this is the basic definition of arch, and what I showed last time is that, first of all, this is a special case of white noise. I also claimed a couple of other things, namely that it exhibits bursts in volatility. To make this case, you just really need to think intuitively about what that equation does. If you have some large log returns, then you have large values of xt squared here, and if you have positive alpha j there, which you always do, especially if you have positive alpha j close to 1, then you tend to get a large sigma t squared at the next point in time, which in turn leads to you being more likely to have a big magnitude value then, which then would get fed back into the next one, and so on. That's how you get your bursts in volatility. So you can just look at this system of equations and see how the bursts of volatility come about. Using a slightly more painful argument, I claimed that it has heavy-tailed distributions. In other words, when you look at xt here, it has a kurtosis that's bigger than 3. So it's heavy-tailed compared to a Gaussian distribution. And that's something that we like because it's consistent with what we actually see in log returns that we observe in the market. Okay, so that's a quick review of the arch process. I talked a little bit about establishing basic properties and about estimation. Estimation here is typically done by maximum likelihood estimation. And we take the likelihood, we use this usual expansion. We would like to take a product from t equal 1 up to n. We can't actually do this generally, of p of xt given xt minus 1 and so on back to x1 along with some parameter vector eta. So this would just be the standard expansion of the likelihood that we've seen a few times in the course. The arch process has this nice property that the conditional distributions are Gaussian, which means each term in this product is Gaussian with a mean of 0, and a variance is just sigma t squared, which you get by applying this formula directly. So it's very easy to compute this thing as long as t is greater than the order p. So for t less than or equal to p, it's kind of annoying to, well, we don't have a closed form solution for this distribution. So instead what we do is we take this thing here, and this is called the conditional likelihood because we're conditioning on the first few observations that we have. Okay. Anyway, so you do maximum likelihood estimation using this conditional likelihood, or really you would use the log of the conditional likelihood because that's better behaved numerically. And then you maximize with respect to parameters, and you can estimate alpha naught, alpha 1, and so on up to alpha p. It would be a constrained estimation problem because you want to make sure that alpha naught is positive and that the other alphas, not only are they non-negative, but they also add up to something that's less than 1. But you just pull in some off-the-shelf optimization algorithm, and that's a pretty straightforward procedure. Okay, so that's estimation in a nutshell. What I didn't talk about, and what's actually a little bit interesting, is forecasting with an arch model. Okay, so let's suppose that we've got our xt process. Think of this as log returns, and let's suppose that we're saying that an arch p model is appropriate for this. Well, unfortunately, that means that xt is a special case of a white noise process. It has mean 0, as we showed before. It has variance, which we established this expression for as well. It's alpha naught on 1 minus the sum j equal 1 to p of alpha j. And we all know that if we have a white noise process, there's no correlation between successive values. So anyone care to tell me what that tells us about our one-step predictors, xt hat? Any guesses here? If I have a white noise process and I want to predict xt given xt minus 1, xt minus 2, and so on, it's actually, well, it would be the expected value of zt. It's actually just 0. So the forecast for a white noise process, the best linear predictor is just 0. So this is actually not very interesting, but it does tell us something rather important about arch processes. It tells us that we're, for example, not going to be able to build a trading strategy that says go long or go short if we're just modeling with arch processes. So these things may be great in the sense that they tell us the conditional volatility, they explain the heavy tails, they explain the bursts in volatility. They're wonderful from that perspective. But at the end of the day, it doesn't actually tell us whether we think it's more likely for the price to go up or down tomorrow based on what we've seen so far. Okay, so that seems like a drawback. Indeed, it is a slight drawback. There is something that it is useful for. We know that for this arch process, expected value of xt squared given xt minus 1 and all of the previous x's, this is the conditional variance of this thing, is just, it's going to be alpha naught plus some 1 to p alpha j xt minus j squared. And this is not the same as expected value of xt squared in this case, which is alpha naught on 1 minus some j equal 1 to p alpha j. Okay, so we'll come back to this in a minute, but basically the upshot is that from an arch model, we're not really going to be able to say whether we think it's more likely or not that the price will go up or down, but we can say something more interesting about tomorrow's variance than we could with a simple ARMA model, for example, that would just say that the variance is constant at some function of this value here. Okay, so we'll come back to that soon. Before that, I want to point out residuals, because residuals for arch models are in fact very simple.
Professor, can I ask you one question?
Yeah, go
Let's
ahead.
say that, is it possible if I use the ARMA model to predict the volatility, and maybe I can use maybe I use Arch model to predict volatility and use ARMA model to predict the tomorrow stock price?
Yeah, that's a good idea. So in fact, that's what I'm going to come back to as soon as I've finished. I'll do residuals and Garch models, and we'll come back to exactly what you're talking about, which is kind of a way of getting the best of both worlds. Okay. All right, but sticking with arch models just for now, we can define residuals really nicely for arch models. If we just take xt divided by sigma t, you notice we go back to our arch equation. Sigma t is computable at, if we have some fitted model parameters, we know the alphas, then sigma t, of course, is computable at time t. So we can just take the x's and divide them by the sigmas, and we should get left with the z's. So this thing is actually equal to zt, and this thing, if the arch model is correct, then we know that zt is IID normal 0, 1. So then if we fitted the correct arch model, then our w hat t will be IID normal 0, 1. And of course, that means that we can take all of the standard residual tests that we just discussed before and apply them to this as well. So all of the tests we talked about before can be applied. Remember, most of those tests were testing for IID-ness. So if you run one of those tests against this thing and it fails, you're rejecting IID-ness. In fact, this is, well, if you reject IID-ness, then you're certainly rejecting IID normal 0-1-ness, because this is an even stricter requirement. So if it's not IID, there's no way it can be IID normal 0-1. So the point is, all of the previous tests apply, including we can look at the QQ plot to see if these things look roughly normal. In fact, that gives us a reasonable sense of whether or not we've captured the heavy-tailed behavior or not. Okay. Now, I'm going to shift over to Khronos in a bit and just show you what these things look like. But before I do that, I just want to define Garch models and explain some of the differences between Garch and Arch models. So Garch models are also autoregressive, conditionally heteroscedastic models, but the G stands for generalized. And the way that they're generalized is simply by modifying the form of the expression for the sigma term. So it's a slightly richer way of describing the evolution of the sigma t squared component. So again, we have xt is sigma t zt, with zt being IID normal 0-1. But this time we take sigma t squared to be the same as before, alpha naught plus sum j equal 1 to p alpha j x t minus j squared, along with an additional term, that is sum from j equal 1 to q of beta j times sigma t minus j squared. So now, in addition to sigma t squared depending on recent squares of log returns, it also depends on its own previous values. So we place some requirements on this. And these requirements, well, I'll just put down the typical requirements that you place here. That's alpha naught greater than 0, alpha j greater than or equal to 0 for j equal 1 up to p, beta j greater than or equal to 0, and we also need a kind of stability requirement as well. So obviously if we could blow this thing up by having alpha j's too big, then we can also blow it up by having the beta j's too big here as well. So normally the requirement is that sum from j equal 1 to p of alpha j plus sum from j equal 1 to q of beta j has to be less than 1. And this condition here, well, along with these constraints here, this thing ensures that a causal solution exists. So if these constraints are satisfied, then you can say that xt can be written as a function of current and past zt's. Again, it's some weird nonlinear function, but nonetheless it's a function. Okay, so this is the Garch model. Let me just highlight the things that you should know about this. So first of all, essentially the properties are pretty much the same as the Arch model. Garch is a special case of white noise. In particular, xt satisfying this Garch PQ equation, well, is going to have expected value of xt is 0, and the variance of xt will be alpha naught on 1 minus sum of alpha j minus the sum of the beta j coefficients as well. Okay, again, xt is not going to be IID. remember we made this argument before. Basically, it has a dependent structure in the sense that because the magnitude of these values exhibits serial dependence, they can't be independent. We also have that the distribution of xt is heavy-tailed. And we have that these things exhibit bursts in volatility. So essentially, it's got all the same properties as before. There's one slightly annoying feature here. That is, because sigma t squared depends on previous values of sigma t squared, it's not immediately obvious how you should get the initial values of sigma t squared when you're doing computations, for example, for the likelihood or for forecasting. So typically, to evaluate sigma t squared, whenever we have sigma t squared, well, whenever we have a term sigma t minus j squared and t minus j is less than or equal to 0, we replace this just by the stationary variance of the process, which is gamma x of 0 is alpha naught on 1 minus the sum of the alpha j's minus the sum of the beta j's. So we do this when t minus j is less than or equal to 0. And as long as we do that, we can always find some initial values of sigma squared to plug into the conditional likelihood and to evaluate sigma t squareds that we might need to use for forecasting. Okay, so it's a sort of hacky approximation. It gives you a way of starting out the sigma t squareds at the beginning of the process, but it's normally a very effective thing to do because normally the sigma t j terms that you need in order to evaluate this thing, they only go back p and q points in time, and p and q are orders that are very small compared to the amount of data that you have typically. Okay, now one more comment on why you would use Garch models instead of Arch models.
Professor, can you move the sheet a bit down? We can't see the...
Oh, yeah, sorry. There you go. So I guess the point here is that when you do this, all of the numerical methods that I talked about just before for parameter estimation, forecasting, apply for Garch just as they did for the Arch models. So normally you make this approximation and then you compute likelihoods just like I did before. Okay, so back to my comment on why you would want to do this. There's a little bit of extra pain because you've got a few more parameters, and you have to make this sigma t squared approximation for small values of t. But the important thing about a Garch PQ as opposed to an Arch is that the serial dependence on the sigmas here can help you in real life. And to think about this, imagine that you're in the height of the subprime crisis and some terrible piece of news has just been released. And what happens is you start to see some huge log returns. Well, there will be those huge log returns with an Arch model. Every time you see one, it will induce a large volatility at the next time point. But in an Arch model, you might just happen to get a 0 as a realization of your log return, for example, if you simulate, or you have a crazy day during the subprime crisis where everything swung a long way up and then came back and ended up at the same place it started. And with an arch model, when you get that 0, it kind of resets the whole volatility, because suddenly the volatility going forward is back to a small value again. Now, the thing about a Garch model is that you could get a realization xt close to 0, and if you're in a high volatility regime, the dependence on the previous values of sigma squared keeps the volatility high, even though you just happen to get a few small observations. So Garch models have slightly more persistent bursts in volatility, and indeed the persistence that they display is much more consistent with real-life market behavior than with an arch model. So that's my quick explanation of the intuitive difference between an arch and a Garch model. And as a result, I'm going to tell you this kind of shortcut rule of thumb, which is kind of silly, but incredibly effective. Usually for financial time series log returns, a Garch 1-1 model works well. So if you're struggling to come up with a model and you have to determine a model with no computing support and you have to do it in 10 seconds flat, the Garch 1-1 model is a good thing to choose. So let's try and shift over to Khronos and have a look at this. All right. All right, so I'm going to pull up Khronos here. If I'm lucky, we'll still have something left in the desktop here. Okay, let's see if we have a whole project. Nope. Unless it's in stuff. Oh, here it is. Okay. Okay, what have we got there? Not sure. Okay, let's see what we got here. Let's see, that looks like the S&P 500, doesn't it? Okay, so here's the S&P 500. Here are the log returns of the S&P 500. This is this example where we were looking at in-sample and out-of-sample behavior. This is our in-sample, and we fit these ARMA models here. So there's the baseline white noise model, and an MA3, an ARMA 1.1, and another MA3. I guess these three are the ones we're interested in. Now, let's say I pull down a Garch model. Now, in Khronos, the sum of squares order is P, and the autoregressive order is Q. So let's go ahead and fit. So the 1, 0 is where P is equal to 1, Q is equal to 0. So this is where the Garch is simply an arch model. So this is an arch 1 model. And then let's grab a Garch 1-1 model. Let's see what the likelihoods here look like. Let me make sure that these are correct. So I'll just refit this one, make sure we get the same thing. Okay, so that's the same. All right, so here we have here's a fitted MA3 with a log likelihood of 2812. Now let's look at a Garch 1-0, which is the same as an Arch 1 model. I'll go ahead and connect this up there. Let's go ahead and fit this model. Okay, so here are our parameter estimates. You can see that alpha 0 is this 0.000173, and alpha 1 is this 0.37 value. So that's telling us there's a positive, well, obviously that thing is constrained to be positive, but it's reasonably significant because it's rather large, it's 0.37. There's a positive dependence of the volatility today on yesterday's squared log return. Now let's just look at the actual value of the log likelihood as well, because keep in mind this is a measure of how likely this particular data is under your model. We can compare this to the ARMA values. So with the ARMA value, with this MA3, we got 2812. With this ARCH1, we get 2867. So the AIC, well, the log likelihood is enormously larger for the ARCH model than it is for the ARMA model. So this is telling you that the ARCH model is getting you a much better distributional fit. It's just a shame that that much better distributional fit is achieved by accurately describing the volatility, and it doesn't actually give us information about the mean. Okay, so let's look at the same thing with a GARCH11. So here's a GARCH11. It's got three parameters, alpha 0, alpha 1 here, and beta 1 here. So let's go ahead and fit that. Okay, now you'll notice something interesting. Well, there are a few interesting things about this. So remember my rule of thumb said that when in doubt, fit a GARCH11. Well, notice the comparison in log likelihood between the ARCH model, 2867, and the GARCH model, 3162. That's a massive improvement. That's just off the scale. So this is saying this GARCH model is a fantastically better description of the distribution than the ARCH model. Also notice the beta term in the GARCH model is 0.9. So that's saying there's a very strong serial dependence between the volatility at one point in time and the volatility at next point in time. And really the log returns are kind of plodding along driving this thing, but it's the current level that matters most in determining the next level rather than the actual particular log return that you see. Okay, so now we look at another thing worth noting is back to our ARMA 03 here. Notice these log returns go through the subprime crisis. You can see in 2008, basically everything goes berserk. So we had this huge volatility. When we compute the residuals, we should see that effect mitigated somewhat. By dividing by the volatility, we should see something that's reduced more to a realization, something closer to a realization of IID normal 0-1s. So with the ARCH model, here are the residuals. So you can see maybe a little bit, but not a huge amount. Now we go to the GARCH11 model. We've seen we've actually done really quite a nice job of collapsing this down to something that looks like it might be a realization of IID normal 0-1s. There's one interestingly large value there that might be worth looking at a bit more closely. I don't know what that is. But apart from that, this really does look like a realization of IID normal 0-1. We could then go ahead and look at our look at residual analysis from this thing, take our standardized residuals, and you'll see here a QQ plot is actually not too far off a straight line. We've got that one very large negative value there, which is a little bit strange. But apart from that, it's actually a pretty close fit to a straight line. You'll also notice just by fitting the GARCH11 model that all of these tests now pass. So we don't have any p-values less than 0.05 there. So it looks like we've explained a lot of what's going on just by capturing the volatility. Okay. Any questions about that?
Professor, do you also
Yeah.
use the GARCH model for forecasting? You say that ARCH is not good for forecasting. What about GARCH?
Okay, again, so ARCH and GARCH are both no good for forecasting the mean, but they are good for forecasting the volatility. So ideally what we would like to do is put those together and make a statement about what the value is likely to be tomorrow. We can come up with the best linear predictor for tomorrow based on an ARMA model, and hopefully we can actually say something about the variance tomorrow as well. And variance is actually, it is actually a little bit useful in trading because, you can imagine if you have something, let's say your predictor is for 0.1% positive return tomorrow. Well, if the standard deviation on that is 3%, that's somewhat worse than if the standard deviation on that is only 1%. So you could imagine in a trading situation, you would certainly prefer to get the same mean if the variance was lower than it was otherwise. Okay.
Do people use this for doing options, like just getting the volatility for options?
Yes, that's another good point. If you're going to price options, then you need to be able to come up with a projection of what the volatility is going to be going forward up to some point in the future. So, yeah. Actually, with options, just doing a simple Garch analysis is probably too simple because there's all kinds of other effects that you want to take into account as well. But I guess that's a story for a different course than mine. But good point. You are, of course, interested in volatility when you're pricing options. Okay, one little word of caution, which I'll write down. And this is up there with the annoying fact that the AICC, you'll see defined two different ways, well, at least two different ways. You'll see it with a positive sign and a negative sign. Some people define the orders P and Q the other way round. So some people use, it makes it even hard for me to actually write this down in a meaningful way. Some people use, let's call their Garch models a Garch prime model, PQ, to mean what in this course would be a Garch QP. So you kind of have to look often at the equation that someone writes down in a Garch model before you actually say what the order is and have it mean something in your own head. Of course, the nice thing is that for a Garch 1-1, this doesn't matter at all. But just keep in mind that sometimes people will define P and Q the other way around from the way I define them in this course. Okay, so that's the quick description of Arch and Garch models. We'll have a break soon here, and I think then we'll be able to knock off everything after the break and call it a day. But what I want to do now is at least introduce the idea, which has been alluded to a few times already by several of you, of ARMA-Garch models. And this is actually a kind of elegant and fairly simple thing to think about. Remember the definition of an ARMA model. If we say 5b, well, if we have a process xt and it satisfies this equation here, where zt is white noise 0 sigma squared, and we do the usual thing of constraining these polynomials, so a causal, well, okay. I haven't talked about invertibility, but you often constrain the roots of theta as well so that your process is invertible. I'm just mentioning this in passing now because it's a common thing you do, and you might want to look it up. It won't be, it's not something that you need to know for the exam or anything like that. But if you constrain these polynomials in the usual way, then this would be an ARMA process. Well, what we often do is we take ZT to be IID normal 0 sigma squared. That's kind of the conventional assumption. If we do that, then our process will be Gaussian. We can evaluate the likelihood in a straightforward way, and we can do everything we want. But you think back to the definition of the ARMA process, all we really need in that ZT there is a white noise process. And rather nicely, the Garch 1-1 model is a special case of white noise. In fact, a Garch PQ model of any order is a special case of white noise. So instead of taking ZT to be IID normal 0 sigma squared, we can take ZT to be something coming from a Garch PQ process. So if ZT is Garch PQ, it's a special case of white noise. If we then plug it into this equation and define a process xt, that will be an ARMA model, assuming the usual constraints on the polynomials are satisfied. We have a causal ARMA model driven by Garch noise instead of by Gaussian IID normal noise. So this is a perfectly reasonable ARMA model. It's just an ARMA model which happens to be driven by Garch noise instead of normal noise. And such a thing is called an ARMA-Garch Garch model. So you can imagine, so on the surface of things, it seems like we have a pretty good idea here, and it is a decent idea. It works, it's perfectly good because we're going to have an ARMA component that we can use to forecast the mean. We know how to forecast for an ARMA model. We can write down the covariance of this thing and solve the prediction equations and so on. Then we get the best linear predictor, and we're all set. But at the same time, there should be some interesting information we can capture here about volatility beyond just using our best linear predictors to get the mean. So let me comment first on the thing which is weakest about this whole thing. And that is, if you want to fit this model, you're in a little bit of trouble because, strictly speaking, if you use the standard ARMA parameter estimation algorithms, they're going to assume that the process is Gaussian, when in reality, it's not. This process here, when ZT is driven by, when ZT is a Garch model, is not Gaussian. When ZT is IID normal, it is Gaussian, but we've abandoned that, and the ARMA Garch model is an ARMA model driven by non-Gaussian noise. That ARMA model is in turn itself non-Gaussian. It will have heavy tails. You're going to see bursts in volatility, and so on. So strictly speaking, it's a slight abuse to go ahead and do parameter estimation for this thing, pretending that it's a Gaussian process. Nonetheless, we can go ahead and do that. So this is the crude approach to doing fitting is step one. You basically fit an ARMA PQ model by Gaussian maximum likelihood estimation, where this by Gaussian maximum likelihood estimation is, write down, dubious. And then step two, we fit a Garch PQ to the residuals.
Are the P's and the Q's the same?
Oh, sorry, P, they're not. Let's call that P prime and Q prime, thanks. And invariably, well, not invariably, but in almost every case that I've looked at, the Garch 1-1 tends to work pretty well here. Okay, so that's the basic idea. And now let's come back to this idea of prediction.
Quick question. Do people do this numerically?
Yes, actually there's different way. Okay, so there's two different levels of fitting this thing numerically. So what I've written down here, I guess there's two separate numerical optimization problems here. These are just the numerical optimization problems that I talked about in the course. If you want to get a bit fancier, you can actually try and lump them together and put all the parameters in one big parameter vector and do numerical optimization of that thing. And you have a slightly more complicated expression for the log likelihood in that case. But yeah, you can try and lump it together. But essentially, this is a numerical problem to estimate the parameters.
In general, is it worth it?
In general, I would say it's not usually worth it to go to the extra trouble of combining these into one big step, because in many cases, the extra dimensions you get to deal with in the optimizer don't really add all that much, and in fact, you can get stuck in weird local maxima. So this procedure is actually relatively stable. So I tend to recommend just this two-step procedure. I think it's a bit cleaner.
Sorry, I meant, is it worth it to fit those, fit those two steps separately numerically versus just doing the Gaussian MLE fitting?
Well, okay, so we have Gaussian MLE. So this is two separate. Okay. Is it worth it to? Are you basically asking if it's worth it to go to the trouble of coming up with a whole ARMA Garch model instead of just sticking with the ARMA model?
No, sorry, maybe we can talk about it later. Sorry.
Okay, all right, we can talk about it later. But it does raise a point. So the ARMA Garch model, if you just fit an ARMA model, it would be my maximum Gaussian likelihood estimation. And you could use that to come up with predictors that you could use to take positions, either long or short. By going to the ARMA Garch model, you actually get more information than just which direction it's going. You get the volatility looking forward as well, and basically that enriches your ability to come up with rules for taking positions. So it gives you a slightly richer set of information upon which to make trading decisions. Yeah.
You're fitting the ARMA model to the time series generated in X, so X data points. What are you fitting the Garch model to?
Okay, so this is the residuals from this ARMA fit. So this is to the log returns, and you fit the Garch model to the residuals of the log returns under the ARMA PQ model, the fitted ARMA PQ. One way to think about this is, remember when we talked about ARMA models, one of the key statements was that if your ARMA model is reasonably good, then the residuals from your ARMA model will reflect properties of the underlying ZT process. So exactly the same applies here. If your ARMA model fitting process is reasonably good, then the residuals from that fitting process are going to reflect properties of the ZT. And because we assume ZT is a Garch model, then we can go ahead and fit a Garch model to the residuals. So the only complaint in this process is that you might be a little bit off in your ARMA model parameter estimates because of the non-Gaussianity.
But won't some of the vol be accounted for in ARMA already?
The ARMA doesn't really capture the varying vol. It'll capture a little bit of moving around.
But a little bit of the constant of the vol, right? So some offset is built into the ARMA. You see what I'm saying? So if you've got some vol and the vol increases, the ARMA won't capture it. I understand that. But if it'll get, quote unquote, the average of the vol across the time series.
Yeah, the ARMA will effectively get some kind of average of volatility across the whole time series. So when you look at the residuals, because you're essentially dividing by something that doesn't capture the time varyingness, you're dividing by this kind of average term, you're still going to have this burst in volatility left in the residual.
So the Garch model captures the relative changes in the vol.
Yes.
But the ARMA is already accounted for some constant offset of the vol.
Yes. So you could look at you could look at either standardized residuals here or non-standardized residuals here. It actually doesn't matter because the Garch model can the volatility can scale to whatever you need it to. So yeah, normally you do it with the residuals, and you let the normally you don't, instead of fitting to standardized residuals, you fit to the residuals themselves because they match the processes, they match the properties of the ZT process directly without a scaling factor. But yeah, I mean, you could effectively do this procedure by putting standardized residuals, and that's where you divide by sigma to make the variance 1. You can really absorb that constant into either the ARMA or the Garch. You just don't want to do it in both, if possible. Okay. So let me just plow through prediction here, then we'll take a break, and then when we finish the break, we can come back and basically just go through the list of all the things you need to know for the exam. So, ARMA-Garch prediction. It's relatively simple. The best linear predictor for xt comes straight from the ARMA model. Right, all you have to do here, the ARMA model determines the covariance function, the auto covariance function. Then you plug this thing into the prediction equations, And from the prediction equations, you then solve, and you can get xt plus 1 hat, your best linear predictor of the log return at time t plus 1 based on current and past. And this will be a linear function of the previous log returns that you've actually observed. Now, the mean squared predictive error, expected value of xt minus xt hat squared, this thing is actually just the same as for an ARMA model. So you remember when we wrote down the prediction equations, I wrote down a formula for the mean squared predictive error. Well, because this is still the ARMA framework, it just happens to have a Garch model as the driving ZT process, the formula still remains valid, and the mean squared predictive error is just the same. So that's a little bit distressing until we realize that it's actually not the mean squared predictive error that we really care about. It's the conditional mean squared predictive error. So the conditional mean squared predictive error is expected value of xt minus xt hat squared given all of the past information. And you can imagine that if we have a choice between just thinking about what would be the variance tomorrow under the model specification as opposed to what would be the variance tomorrow under the model specification, assuming that we're given all of the past information, obviously you want to use as much information as you can. So the second one is clearly preferable. With the ARMA models, these two things are virtually the same, or they converge fairly rapidly to being the same over time. So the whole issue doesn't arise in the context of ARMA modeling. But because we have a Garch model here, there's some extra information, there's some use in going beyond the mean squared predictive error and looking at the conditional mean squared predictive error, which is the variance tomorrow given all of the current and past stuff. So to get this, what we do is we just compute residuals from the ARMA process let's call these residuals W hat T. And then we simply take the expression for the one-step predictive conditional variance in the Garch model and evaluate it as sigma T squared, and I guess I should put a hat because we're estimating something here. This thing will be alpha naught plus alpha 1, plus sum of alpha j. It would be xt minus j squared. Now we're saying that the residuals are going to be a proxy for the ZT process, which is the Garch. So we put in our residuals from the ARMA model here. We have W hat T minus j squared plus sum beta j of sigma hat T minus j squared. So it's very simple. And again, we use this argument that that if our ARMA model is kind of halfway okay, then the residuals should reflect the properties of the underlying Z process, which means we can take the residuals, and if they represent the Z process, we plug them into our standard Garch formula to work out the variance going forward. Okay. So that's the procedure. Now, on that note, that's basically all of the material that you need to know for the course. And I think we've got some food here. So let's take a 10-minute break here. We'll try and keep it relatively short so as not to leave you all hanging too long in Pittsburgh. And when we come back, I'm just going to plow through all of the stuff you need to know for the exam. So think of questions on material required for the exam in the next 10 minutes. Okay, let's go ahead and gather for the last part of the course. Okay, so what I'll do now is basically just go through the ground rules for the exam and then give you a kind of summary / list of all the things that you're responsible for knowing. And then after that I'll take questions if there are any. So first of all, the exam itself is 3 hours, May 9th, 5:30 to 8:30 p.m. You can bring 2 pages, 2 double-sided or 4 single sides of handwritten summary notes. You can write whatever you want. If you, so you can go through the notes and basically copy down anything that you think could conceivably be useful. In the exam, you can apply the results of any theorems that are in the notes. So if you want to do that, you just quote it and then apply the results. The basic rule is that a raw score of 90%, and when I say 90%, I mean raw score of exam plus homework, guarantees an A for the course. You should keep in mind that time pressure could be a constraint. If you look at all the problems on the exam and you don't know how to do them and you end up leafing through your summary sheets trying to work out on the spur of the moment what approach to use, you might find yourself a little bit squeezed. So usually time can be a pressure for some fraction of the class. If you work through the practice exam and you can do that pretty comfortably in 3 hours, then you should be in reasonably good shape. So my recommendation is, first of all, work through the practice exam, and secondly, make sure you understand all the homework. And the other rule is no calculators, phones, laptops, or any other electrical devices are allowed. Sorry?
Meaning we won't be needing them, right?
Yes. Arithmetic will be set up to work out nicely, which incidentally gives you a little bit of a hint as to whether you're on track or off track on a particular problem. Also, you won't need to invert anything bigger than a 2x2 matrix, but you may need to invert a 2x2 matrix, so you should know the basic formula for that. Okay, so those are the basic rules for the exam. Now, in terms of material, basically, there's all of this stuff that we covered in the actual lectures. Most of it you should know. I'll go through the list now. You'll notice there's a few sections of other things in the notes. If it's in the notes but it's not on this list, then you don't need to know it. So things that you should know include, of course, the good old autocovariance function and its normalized version, the autocorrelation function. Remember, we use the autocovariance function basically to come up with a definition for stationarity. That's weak stationarity. You don't need to know about strict stationarity, although you're welcome to review it. Then in addition to the autocovariance function and the autocorrelation function, which are properties of a process, we looked at the corresponding properties of data, namely the sample autocovariance and the sample autocorrelation. So these were really all the preliminaries in terms of definitions. Now, after this, we looked at transforms to stationarity. So the basic idea is that most of the things that you observe in real life aren't actually realizations of stationary processes, but could be viewed as something which, with an appropriate transformation, would be a realization of a stationary process. So things to know here are the structure of the classical decomposition, and basically this two-step procedure to convert things to realizations of stationary processes, which is usually take logs or not. For a number of time series, you don't need to take logs. And then after that, then typically you'll do one of two things. You'll either apply differencing methods to come up with a stationary process, or you'll specify some kind of parametric structure for the classical decomposition and then do least squares estimation of the components in the classical decomposition. So this is the typical approach. You should make sure you're familiar with that. Then after this, there were two classes of processes that we looked at, which are quite important. There's linear processes. So these are very important. This is where you take a white noise process and apply a linear time invariant filter to it. And one of the nice things about these was that you can apply theorem 181 in the notes to get the autocovariance function of the resulting process. So as long as you can express your process as a linear process, you have a reasonably well-defined machinery for working out the autocovariance function. Beyond linear processes, we also looked at Gaussian processes. So these are very important. They keep cropping up again and again. There's a few things, obviously, involved in thinking about Gaussian processes. First of all, there's a whole lot of rules for working with the multivariate normal distribution. So I guess you've applied a few of these in the homework. There's the multivariate normal density, which is really what you use in order to do likelihood computations for Gaussian processes. So really, the assumption that you have a Gaussian process makes life very easy in analysis for various reasons. One is you have these very simple ways of transforming Gaussian processes. For example, you multiply a multivariate normal vector of elements by a matrix, and you get another multivariate normal with a different mean and a different covariance. The density is kind of straightforward to compute. There's a bit of numerical stuff there, but basically armed with the fact that something is a Gaussian process, it makes it much easier to do parameter estimation and to do various other manipulation as well. Okay, so these were kind of two broad categories of processes beyond just thinking about stationary versus non-stationary processes. Then we looked at the problem of prediction. In terms of prediction, you need to know, of course, what a best linear predictor is, and how to get it using the prediction equations. So remember, prediction equations, you just construct this big matrix with the autocovariance structure contained in it, and then you solve a system of linear equations, and you get a bunch of coefficients that you apply to past data to predict future data. As I mentioned before, you should be able to solve 2x2 systems of equations by hand. So there's a formula for the inverse of a 2x2 matrix that you can write down pretty easily. You won't be given anything 3x3 or worse, because then you just spend too much time doing tedious arithmetic. And along with getting the best linear predictor, you also want to get the mean squared predictive error. And in the context of GARCH models, you should be thinking about conditional mean squared predictive errors rather than just mean squared predictive errors. Okay, so then I guess a bulk of the course has actually been spent talking about various aspects of ARMA models. And there's lots of components here. First of all, you need to know the definition, and then how you check for existence of a stationary or causal solution, or stationary and or causal. You should know how to find the autocovariance function for a given ARMA process. We had this other result which tells you how to determine the autocorrelation function of an MAQ process and the partial autocorrelation function of an ARP. We described how you use the assumption of Gaussianity to compute Gaussian maximum likelihood estimation. I also covered briefly the idea of Ewell-Walker estimation. You should review that. Ewell-Walker estimation is pretty simple and not as efficient as Gaussian maximum likelihood estimation, at least not when the process really is Gaussian. But it's kind of elegant and simple to get quick estimates, especially for an AR process using Ewell-Walker estimation. And then we talked about order selection, that is choosing P and Q. I guess really there were two ways. One is using this result up here. And the other approach is using the AICC statistic. So that's all the mechanics of basically model fitting. Then there's also residual analysis. So in residual analysis, basically we have the property that if you get the ARMA model correct, then when you compute the residuals under the assumption that that's the model that generated the data, the residuals that you see should reflect the properties of the ZT process in the model. So they should look at least like white noise. If you assume that the Z process was Gaussian, they should look like Gaussian white noise, Gaussian IID noise. Okay, so residuals, you need to know the definition, obviously, and then tests for IID-ness. You should basically know how to derive these properties of the test statistics and also how to interpret results. We looked at a few of these. There's basically the simplest thing you can do is inspect the sample ACF and PACF of the residuals. And remember here, basically you look at the residuals, and if they are indeed a realization of something IID, then you should see only 1 in 20 of the sample ACF and sample PACF of the residuals coming a little bit out of the blue bands, or the dotted lines, whatever your computer package is giving you. There's the portmanteau tests. So these are basically the Leung-Box test and the McLeod-Lee test. You should understand the distinction between those two things, what they're testing for. And then to test for normality, you can look at a QQ plot as well. So you should know at least those ones, but you should in general be familiar with the kind of concepts that you need to use when you're testing residuals. Then there's ARMA models. I'll just write ARIMA models here. You should just obviously know the definition and know how to recognize one. Well, that's really stated in the definition. Something that you difference and end up with an ARMA model. The original thing is an ARIMA model. So ARIMA models are a natural, non-stationary extension of ARMA models. We'll go to 8. Then there's Arch and Garch models. So you should know the basic properties of these things. Essentially, we established that these are special cases of white noise and a few other things. You should know these basic principles, how to derive these properties. So it's conceivable you could come up against a question that might need you to use these double expectation type arguments. You should know how likelihood computation works, and hence how you would do parameter estimation. Obviously, I'm not going to get you to actually do any numerical optimization in the exam, but you should know how to at least compute the likelihood, and you should know how to get the residuals and interpret them. Okay, so this is much of the modeling component. Well, this is pretty much all of the modeling component of the course. So the only other thing is a little bit of trading strategy development. Again, since I didn't really get into this in great depth, it will be relatively light, the amount of knowledge that you need for the exam on this front. Basically, you should know what to do with predictors. In other words, well, that's pretty obvious. You're generally predicting whether something's going up or down, so hopefully you all know that if it's going up, you should buy. If it's going down, you should sell. There's other details, of course, on exactly what you can do, but that's the basic concept. The one kind of quantitative thing that you really should make sure you understand with trading strategy development is how to evaluate the Sharpe ratio. And also the distinction between the Sharpe ratio and the realized Sharpe ratio for a given strategy. Okay, so that's basically it. If you know all of this stuff inside out and you can work through problems based on this reasonably quickly, then the exam should be fine. So let me take any questions that there may be, and then we'll call it quits.
Can you talk a little bit about, so you can make predictions with the ARMA Garch model. So how do those predictions compare with prediction just by ARMA models?
The way you want to think about that is your prediction from ARMA model is basically xt hat is equal to something, and then you have the mean squared predictive error is equal to something else. But with an ARMA model, you'll see that this thing basically is practically constant. So it's really only different at the very beginning for small t when you haven't got a lot of data. So really all you're getting from an ARMA model prediction is xt hat. Now, from an ARMA Garch model, you get xt hat and you get conditional MSPE. And both of these contain useful information. Essentially, in the ARMA case, the MSPE doesn't really contain much useful information because that just reflects something that's pretty close to the stationary variance of the model. In this case, your mean squared predictive error is going to really vary quite noticeably depending on the magnitudes of recent log returns. So it means that, so for the point of view of trading, an ARMA model, it kind of tells you whether you should be long or short, but it doesn't give you much information. With an Armour-Garch model, you can try and make decisions about how much risk you want to take because you have a sense of what the variance is going forward as well. Does that make sense?
Yeah. And are there fancier models that people use?
Sorry, are there what?
Are there fancier models that people use?
Oh, fancier models than this? Yeah, certainly. So there's a number of directions that you can go in. Well, what are some of these? Well, first of all, the big family of models that probably would be most important to include in the curriculum next, if I had more time, would be multivariate models. In particular, multivariate Armour models. So these are models where you have, instead of a sequence of numeric observations, you have a sequence of vector observations. And if you're just looking at two things at once, for example, say, you might be looking at, say, S&P 500 futures along with NASDAQ futures as well. If you're doing that, you might be, well, there's obviously some connection between those two. The price moves are reasonably highly correlated. So in that kind of a circumstance, you would probably want to look at multivariate Armour models. Another big family of models, well, there are lots of families of models. One other family that I could have talked about in addition to Arch and Garch models is stochastic volatility models. Stochastic volatility models are actually very similar in terms of what they say to Arch and Garch models, but the formulation of the model itself is a little bit different. And the numerical methods that you need are somewhat harder. Yeah, that's kind of a beginning. But yeah, there are indeed many other models. So yeah, we've only just kind of touched the tip of the iceberg here. And I've kind of restricted attention to classic ones that have been around for a while now. But certainly if you do a literature search, you're going to come up with lots of stuff. Okay, one question at this end.
What's a procedure for dealing with missingness?
Oh, missing data. Yeah, that's another good point. That's another thing I didn't cover. Okay, I think I can explain it kind of in a really concise little nutshell here. One simple case of having missing data would be if you had, say, imagine you have x1, x3, x4, right? So you're missing x2. Well, there are sort of two ways that you can attack this problem. One is you can say that the likelihood, you can factorize the likelihood as just x4 given x3, x1, px3 given x1, p of x1. In other words, you can use this telescoping expansion. In general, though, these things here will be a little bit difficult to get, but you can actually get these things using what's called a state space representation of the model and something called the Kalman filter, which I guess many of you have probably heard of. That can help you to compute these sort of slightly weird components of the likelihood. Another thing is the Gaussian assumption can save you here. Because remember, if you assume your process is Gaussian, then x1, x3, x4 is just multivariate normal. It'll have a covariance matrix that looks a little bit different from the usual one that you write down. It'll essentially have a couple of, have a row and a column kind of collapsed out. But once you can say that it's multivariate normal, you can compute the density and work with it anyway. So yeah, these are kind of two standard ways of dealing with missing data.
If you assume Gaussian, could you just assume that it's the mean? Is that a safe assumption to make?
If you don't have very many missing data points, you can just fill in the missing data points by the mean of the process. Yeah. So actually, people do that. If you have a lot of missing data, it becomes a bad approximation. But if you're like missing 1 in 100 data points, that's actually a pretty nice thing to do. Okay. Anything else?
One more question, Professor.
Okay, one more from Pittsburgh.
When you say that the process is ARMA, let's say ARMA 1, 2, do you also assume that it's already stationary?
Yes, so implicitly, that's actually something you often forget about, is in the definition of the ARMA model, we say that it has to satisfy the difference equation and also be stationary. So certainly, like on the exam, for example, when I talk about ARMA models, you can assume it's stationary unless the question says, prove this is stationary or not.
How do you go about deciding how much size you should put onto these positions? Like how confident you are in your prediction?
Okay, so I'm afraid I have to kind of avoid answering that one directly. Step number one is experimentation. So try out a lot of different things, see how they work in backtesting. Evaluate Sharpe ratios, look at drawdowns, which I didn't talk about. It's just this biggest, lots of you probably know what they are. It's just the biggest drop in your P&L looking back. So I'd say, I'm sorry, the best answer I can really give is it's certainly something you need to think about. And if you experiment with a lot of different strategies, I think you start to get a feel for what's good and what's not so good. Okay. Any other questions? Sorry? Oh, sorry. No, I can't help you with stochastic calculus. Okay. Well, in that case, so thank you all for listening. I'll point out that we will be monitoring Blackboard discussion somewhat more closely in the coming days. And good luck with all your exams.
I think you mentioned.
One more question?
Yeah, sorry.
Okay.
I think you mentioned earlier in the term that on the last lecture, maybe you'll tell us a little bit more about what you did during your own day trading.
Oh yeah.
I don't know if that's
still. I can give you a very quick summary of my own day trading. Essentially, I traded three classes of futures. Gold futures contracts, oil futures contracts, and Aussie dollar. I traded the Aussie dollar more out of sentimentality than any other reason. I set up a little system, a little home system that was set up on 2 or 3 computers as a kind of distributed system, which would one computer was dedicated to recording prices from the Interactive Brokers live feed. Another one was basically running my little trading strategies and making live decisions. And then the server was then taking orders and passing them through to Interactive Brokers. So this would be automated. One nice thing about my day trading exercise was I stopped all trading by 11 a.m. So I could relax and have a nap in the middle of the day if I wanted to. The predictive signals I was generating were in fact based on ARMA 1.1 models. It's a little bit more complicated. I won't give away all my trade secrets, but ARMA 1.1 models did make an appearance in there. Another interesting lesson, actually, well, there were lots of interesting lessons. One was not to panic and override my own system when things appeared to be going badly. So after 9 months, I looked back and I did a little analysis of the times when I'd intervened in and overridden my own trading strategies. It turned out pretty much about 80% of the time intervening was the wrong thing to do. So that cost me a bit of money in the end. Another thing, ironically, the Aussie dollar I originally included out of sentimentality, but in the end, my strategy for that worked better than the other two, even though it didn't look better in backtesting. So one of the lessons is backtesting kind of gives you a hint of what may come, but doesn't really necessarily, it's not necessarily a reliable statement about how you'll perform going forward. That's the quick summary. I can't think of anything else particularly, anything else really obvious out of that to report on. But if any of you do have general questions about trading, feel free to email me in the future. I can try to answer them as best I can. I'll probably answer them based on my day trading experience. Well, I certainly will answer them based on that rather than on 2 Sigma experience. But I'll see what I can do to help. Okay. All right. So thanks again, and good luck on the exams.